So, we are done with the concepts for this week, week 6, and in this week we learned about displacement current, we learned about conservation laws involving electric and magnetic fields. Then we also learned that E and B, or let me write this, EM fields carry energy, linear momentum and angular momentum. And finally, we also explored a little exploratory discussion we had in one lecture about magnetic monopoles. So, I end this lecture by solving 2 or 3 problems on all these topics. So, the first problem that I am solving is taken from Zangwill's book, problem number 14.12, and it talks about a magnetic monopole detector, and this is also related to the discussion we had about the detector in the lecture on monopoles. So, whatever I asked you there, it will help you understand that also. So, this problem says an ohmic wire with resistance R is bent into a closed loop. Suppose a magnetic monopole with magnetic charge G approaches Earth from a distant galaxy, then it passes through this loop and then continues its way to another distant galaxy. The question is how much electrical charge flows through the ring during this process. So, let us see what is happening. What is happening is you are given a kind of a ring and a monopole G passes through it, and what we want to know is how much charge would have flown through this in the process. What is the physics behind it? Physics is quite simple. If I look at this monopole at certain point, it has all these field lines coming into this area, and this gives a flux phi b. As the monopole approaches, the flux changes, and therefore, there would be a current, and as it goes away, the flux changes again. Right. So, let us make this on the other side. Here are the field lines. Flux will be changing again, but you may ask, that may give you a current in the other direction. So, how come there will be net charge flow? What is important is that as this charge, I was making it with green, so let me do that. As this magnetic charge passes through the ring, its flux changes by a finite amount delta phi, and that gives a kick, which gives you that charge going around. And now, when we solve it, we will see it. So, physics part is that. Now, if I take this loop, and here is this magnetic charge G, at some distance, let us say the line crossing is the origin, then the flux phi due to this would be, so let us see that, these are the lines coming through. If I take a small area here, some ds, right. So, this flux would be equal to ds dot r over r cubed times mu 0 over 4 pi g integrated over, because B field is mu 0 g over 4 pi r cubed r vector. So, let us see what is happening. What is happening is that I have this loop, magnetic charge G, and it has all these lines coming through, B field lines, and I am taking the straight line down where it crosses as the origin. Then if I take a small area ds, then the flux is given as mu 0 g over 4 pi integration ds dot r over r cubed, and this is nothing but mu 0 g over 4 pi integration d omega. Right. To understand that, let us see how I got that. So, here is this area in this loop. Let me make it at an angle. Here is this red ds, which is pointing one way, and here is this charge. This distance is r. Then the solid angle formed is this right here, shown by blue, by the projection this of area perpendicular to r, and that projection comes out to be ds dot r. Right. So, projection of that area is ds dot r divided by r square times r, because I want to multiply by that r unit vector, and this is d omega. And this is what I have used. So, all I need to do is calculate this change in omega, right. So, delta phi is going to be equal to mu 0 g over 4 pi delta is solid angle change, and that is what I need to calculate. So, let us see what is happening. I will, without any loss of generality, I will take the magnetic charge to be coming along the z axis, and here is this plane. I am taking ds dot r, so it does not really matter how I make it. All I need is that plane projection perpendicular to the direction of motion, and let us see what is phi. Phi, when r is equal to infinity or z equals infinity, this is very, very far away, is going to be 0, and phi increases as g approaches the ring. Then I am going to show that phi, when r is equal to z equals 0 plus, that means the charge is right above, slightly above the ring, is going to be equal to, or let me also write 0 minus is going to be equal to plus or minus 2 pi. So, as it crosses the ring, the change in the flux is going to be 2 pi, and then phi final is again going to be 0. So, all that is happening is that delta phi is going to be equal to, or not phi, this is omega, sorry, I should have been writing omega. Phi is times mu 0 g over 4 pi. So, delta phi is going to be equal to 4 pi times mu 0 g over 4 pi, which will be equal to mu 0 g, and therefore, q is going to be delta phi over r equals mu 0 g over r. I am anticipating the answer, giving it to you. Now, let us do it step by step. So, when this fellow is approaching, I have r I is equal to magnitude wise d phi over dt, d phi b, the minus sign. So, r I dt integrated over is going to be delta phi b, and therefore, q, which is integration I dt, is going to be delta phi b over r. And for that, I need to now calculate the solid angle. So, let us now do that. to facilitate the calculation, wherever the charge comes, right here, I will take this to be the origin. I will take a distance slightly above to be z prime. So, here is this charge sitting right above the plane, and I take this small area somewhere pointing in the z direction. That I can do without loss of generality, z unit direction, and this is ds. ds is s ds d phi cylindrical coordinates, and what I am calculating is omega equals integration d area dot r over r square if it is at a distance r. Since I am taking the origin right underneath the point where the point where the charge is, I can make things easy. So, what we are going to do is like this. Here is the origin. Let me make side view right here. This height is dz, and somewhere at an angle phi is this ds pointing in the z direction. So, I am going to have omega equals integration ds becomes, the area becomes s ds d phi is in the z direction. Point where it is at some vector s minus z prime z divided by the distance between the 2 points, right. So, that is going to be r square, which is going to be s square plus z prime square minus 2 s z prime cosine of phi. This would have been the square, but since I have written this as a vector on top, it will become cube. So, it becomes 3 by 2. The integration is, let me write, s integration is from 0 to some distance r, and phi integration is from 0 to 2 pi. That is the answer. So, what we have done is, we have taken a projection like this. Now, you may ask, what if the disk was, or the ring was, a little tilted, then I would have taken that perpendicular direction to be the z direction. So, it does not really matter. So, I can very safely say that the direction perpendicular to the plane of the loop and going towards the magnetic charge is z direction, and then rest of the calculation follows. Now, keep in mind that z prime is tending to 0. So, s square plus z prime square is much greater than 2 s z prime. So, I can do a binomial expansion and get omega equals integration 0 to 2 pi d phi integration 0 to r s ds. Then I have z dot ds is 0. So, I get minus z prime divided by s square plus z prime square 3 by 2, and then I can do the binomial expansion and write the rest as 1 plus 3 s z prime cosine phi divided by s square plus z prime square, and stop here. That is the answer. So, let us work this out. Remember, what am I working out? Here is this loop, here is this charge particle, magnetic charge particle coming, it is right above this, and the perpendicular direction we have taken to be z. So, I am calculating omega to be 0 to 2 pi d phi integration 0 to some radius r s ds. I have minus z prime divided by s square plus z prime square raised to 3 by 2 times 1 plus 3 s z prime cosine phi over s square plus z prime square. Now, I have integration d phi cosine phi 0 to 2 pi equals 0. So, second term gives me no contribution, and therefore, I have omega equals integration d phi, there is a minus sign in front, 0 to 2 pi integration s ds z prime over s square plus z prime square raised to 3 by 2 0 to r. So, z prime is very small, z prime is tending to 0 and r is some non-zero number. So, I can take s now equals z prime tangent of theta, and then omega comes out to be minus integration 0 to 2 pi d phi 0 to pi by 2, because z prime is tending to 0, r is always greater than z prime. So, tan theta becomes infinity, theta becomes pi by 2, and I have z prime tan theta, z prime secant square theta, z prime d theta divided by secant cube theta, z prime cubed. Now, I can cancel terms. Z prime cube cancels with this, secant square theta gives me secant theta, and this comes out to be minus 0 to 2 pi d phi integration sin theta d theta 0 to pi by 2, and this is minus 2 pi, the first term, and then I have minus cosine of theta 1 0, and this comes out to be minus 2 pi. This is when the particle or the charge particle, magnetic charge particle, the monopole is above. If z prime is equal to 0 minus, then I will get omega equals plus 2 pi. So, let us see what is happening now is that given this loop, as this particle comes through, phi initial or omega initial is equal to 0, it increases, comes all the way up to minus 2 pi here, and then switches over and becomes plus 2 pi here and goes to 0 again. So, phi has changed in the process from 0 minus 2 pi 0 to minus 2 pi to plus 2 pi to 0. So, delta omega is actually 4 pi. Therefore, delta phi is going to be mu 0 g over 4 pi times 4 pi, which is mu 0 g, and total charge q therefore, is delta phi over r, which is mu 0 g over r. That is the answer. This should, as I remarked earlier, help you to understand the superconducting monopole detector better. The only difference between this problem and that is the difference being that R is 0 for superconductors. So, inductive effects become important, and you will have L, the inductance, in your answer. That's problem number 1. Let's go to the next problem. This again has to do with forces on monopoles, and problem number 2. This is also based on the discussion on monopoles. So, question I am asking is, in the lecture on monopoles, we said that in the problem figure shown, and that is this figure, where I had a U-shaped magnetic charge conductor and a rod with E field coming out of the page and the rod being pulled with speed v as shown. So, in this case we had said that the current flows counterclockwise like this, and the force on the current is minus q m v cross E over c square. Question I am asking is, does Lenz's law still hold? The current direction is opposite to what happens in the case of Faraday's law, and there we have Lenz's law, right. In this case, does the Lenz's law still hold? In other words, you see here what we had used was that the magnetic field times dl integration or magnetic EMF was plus d phi e by dt, right. There is no minus sign, and the Lenz's law had EMF equals minus d phi by dt, and there was this minus sign here, which we said is Lenz's law. The question is, does Lenz's law still hold? So, let us look at the solution. If you just to give an answer, you would say yes, indeed Lenz's law must hold, because by opposing the change, energy conservation is guaranteed. So, it must hold, but we have to show now how with that positive sign. So, let us do that. So, I have this circuit, magnetic circuit if you like, with all these uniform E coming out, and the current we are saying is going like this. So, the magnetic charges are moving like this, and the rod is being pulled like this. So, first answer is that, remember, the force on magnetic charge E m is the minus sign v cross E over c square, and therefore, the force on charges, when I say charges, magnetic I mean, in the moving part, right, v is going up, E is coming out. So, v cross E, this will be v cross E, and this will be minus v cross E. Moving charge, so force on the moving part opposes the motion, and that means we must pump in energy to keep the rod moving, and therefore, energy conservation is true. We are pumping energy, which then comes out and gives motion to these charges. Second way to understand this, and I raise a question also here, is what about change in flux, and in this time flux of E field being opposed, because that was what Lenz said, that the change of the magnetic flux in Faraday's law is opposed. That would also happen, because remember, we have curl of E equals minus mu naught j m. This minus sign comes here. I point out minus sign comes here. So, the counterclockwise moving current, which I have shown, this current will give a field not coming up, but going down. This will be the E field generated. So, conclusion is that field given by current, and we mean magnetic current, opposes the increase in phi E, that is flux. So, that means Lenz's law holds. You see, it should not be a surprise that the equations are such that Lenz's law holds, because it is basically the conservation of energy, and if the conservation of energy does not take place, I can make a perpetual motion machine, or I can get a machine that will keep giving me energy once started. That cannot happen, and therefore, Lenz's law must hold, and the signs in my equations would be such that they make sure that this law holds. Problem number 3. This is also from Zangwill's book 15.22, and it is about the angular momentum of the electromagnetic field in a two-dimensional magnetic field. And it says a point charge q is at the origin. A magnetic field B x y pointing in the z direction fills all space. Show that the field, when we say here field, I mean electromagnetic field, angular momentum is L E m equals minus q over 2 pi phi b z, where phi b is the flux of B through the plane z equals 0. So, what you are given is in this coordinate system, where I have x, y and z, there is a charge q sitting at the origin, and all over the place I have this uniform field. I will make these lines randomly, because this is B, which depends on x and y. So, its strength may change at different points, and it is pointing in the z direction. So, I have this magnetic field, and I want to calculate the angular momentum corresponding to the field of this electric field given by the charge and this magnetic field. L E m is given by epsilon 0 integration r cross E cross B integrated all over the place. How does this come about? This comes because I have 1 over mu 0 E cross B as the pointing vector. Then I have pointing vector over C square, which will be epsilon 0 E cross B as the momentum, I should say linear density. And then you multiply r cross momentum density integrated all over the volume gives you the total L E m. So, I have L E m as equal to epsilon 0 r cross E cross B dV, where E is going to be q over 4 pi epsilon 0 r unit vector over r square. B is given to be B x y, it depends only on x and y in the z direction. So, you can say that this is this does not depend on theta. So, B actually depends only on r and phi in the z direction, or even better, B depends on r sin pi by 2, which is basically the coordinate in the x y plane. I can also write it as B s phi, right, where s and phi belong to the cylindrical coordinate. S is nothing but square root of x square plus y square, phi is tan inverse y over x. So, it depends on that only. So, let us calculate E cross B. E cross B is going to be q over 4 pi epsilon 0 r square r unit vector cross z unit vector B x y. I am doing it using spherical coordinates. So, this is the z axis and here is the r unit vector, this is theta. So, r cross z is nothing but sin theta in the minus phi direction, and therefore, E cross B is q, a constant, over 4 pi epsilon 0 r square B x y with a minus sign in front, sin theta phi unit vector, and therefore, r cross E cross B is going to be minus q, this should be r full vector, over 4 pi epsilon 0 r square B x y sin theta r full vector cross phi. R full vector cross phi is in theta direction. So, r full vector cross phi is not theta minus theta direction. So, it is going to be minus theta unit vector times r, because r and phi are perpendicular and r is the magnitude. So, I get r cross E cross B as plus q over 4 pi epsilon 0 r, 1 r cancels, B x y sin theta, theta unit vector. So, we have now got r cross E cross B, all I have to do is now integrate it. So, let us do that. So, I have gotten r cross E cross B as q over 4 pi epsilon 0 r B x y sin theta, theta unit vector. So, L electromagnetic, which is epsilon 0 integration r cross E cross B dV is going to be equal to epsilon 0 is going to cancel. I get q over 4 pi integration B x y sin theta, theta unit vector over r dV. dV I am going to write now in spherical coordinates. It is r dr d cosine theta d phi. Let me write the theta unit vector explicitly. It is minus sin theta z plus cosine theta cosine phi x plus cosine theta sin phi y. Now, I am going to integrate. So, z component of LEM is going to be q over 4 pi integration B x y, I can write as s phi sin square theta with a minus sign in front, r dr d phi cosine d of cosine theta. I cancels 1 r, the r square here. So, this and this together give me an r. That is how I got this. Okay. And the x component would involve an integration sin theta cosine theta d of cosine theta. Y will involve sin theta cosine theta d cosine theta, and both these integrals are 0. So, theta integral gives me 0 for x and y. So, the only component that survives is z component. So, I have L E m in the z direction with a minus sign in front, q over 4 pi integration b s phi sin square theta r dr d phi d cosine theta. Now, since b depends only s and phi, I can write sin square theta dr times r as r sin theta dr sin theta, which is s ds, and therefore, L E m is equal to minus z q over 4 pi integration b s phi s ds d phi d cosine theta, minus 1 to 1, 0 to 2 pi. And this is very easy to interpret. So, let us do that on the next slide. I have L E m is equal to minus z q over 4 pi integration b s phi s ds d phi 0 to 2 pi, s is going all over the place, right. S integration is from 0 to infinity times minus 1 to 1 d cosine theta. This is 2. So, I get this answer to be minus z q over 4 pi integration b s phi d, the area, which is minus z q over 4 pi integration b dot ds, the area, where ds is dx dy in the z direction or s ds d phi in the z direction. And this is nothing but the flux. So, I get L E m equals minus z q over 2 pi times phi b. In hurry, I made a mistake here. This should have been q over 2 pi because this factor 2 here. That is the answer. Let me just conclude this lecture that we solved 3 problems involving E and B that talk about various mechanical quantities associated with these fields. Thank you.